All right, physics students, in this video we're going to talk about the concept of work. And I should point out that your concepts of work in common everyday language are probably a little bit different than the concept of work in physics. And you'll find out why in just a minute. For example, you sitting here watching this video and doing your physics homework, you may feel like you're doing work, but in fact in the physics sense you're not doing any work at all. And I'll explain why that is, okay? So first thing I want to do is talk about forces and displacements and just go ahead and define what work is. Work in the physics sense is what is done on an object when a force is applied to it over a distance. Now, it sounds like kind of a weird esoteric kind of definition. It will make sense as we go through the video very shortly what exactly I mean by that. The symbol for work, the variable for work, is a big W. Very, very, very important. Okay? In other words, and more specifically, work is the product of force and displacement. Okay? Now, force and displacement are both vectors. Turns out that work is a scalar. Okay? And the only way that you can have this happening is if it's what's called the dot product between the two vectors. Okay? So F dot S as vectors, that's how we say that in mathematics, okay? What that means is that we take the magnitude of F times the magnitude of S, and we multiply it by the cosine of the angle in between those two vectors. Now, the unit of work is Newton times a meter, which is called a joule, symbol J, okay? The cosine theta term ensures that there is a common component between F and S, a common parallel component between the two vectors. And that will be obvious as we do some problems dealing with right triangles, okay? The dot product of two vectors therefore returns the product of the parallel components. Work can either be positive or negative. And the positive or negative indicates really which entity is doing the work, okay? So the positive or negative can actually be pretty important. Generally, we kind of don't really consider the negative work. We just kind of deal with work as a magnitude and not really worry about the positive or negative. You'll see why later. Okay. So a simple case. There's a guy here pushing a car. He's applying a constant force over a distance, a displacement S. Okay. A couple of things to point out. If the displacement is 0, the car doesn't move, then no work is done, obviously. That's also kind of like saying if the force is 0, if there's no force applied, there's no work done. Nothing's happening. If nothing's happening, then there's no work done, and there's no physics to really think about there, okay? All right. A little historical note for you. This is actually going to end up to be pretty important for us later when we talk about gravitational potential energy. The term work was introduced in 1926 by a French mathematician Coriolis as the weight lifted through a height, okay? That will be very important later, okay? This person, Coriolis, actually he did some work with the way things move on the surface in the atmosphere of the Earth. In the northern and southern hemispheres as you get farther away from the equator, and some of the work that he did is actually quite useful. The Coriolis force, for example, in atmospheric science. Okay. So again, important. If F and S are not in the same direction, you have to figure out the component of F that is in the same direction as S. But the cosine theta term in that previous equation takes care of that for you. Okay. As an example, there's a girl pulling a suitcase at an angle theta, applying a force to it through an airport. Okay. All right. Here's a free body diagram of that suitcase where the wheel is the center of the free body diagram. Okay. You can see that F cosine theta is the component of F that is exactly parallel to S. Okay, so that's what I mean when I say that the cosine of theta takes care of this issue for you. Okay. Now the concept of work is so fundamental that it's basically used to define what a joule is, and a joule in physics is when the work done by a force of 1 Newton when it moves through a distance of 1 meter in the direction of the force. So that means that 1 joule is 1 Newton meter, as I pointed out previously, or 1 kilogram meter squared per second squared. Okay? All right? Now, I need to point out something really important for you here very early. The joule is the SI unit for work. It's also the SI unit for energy. But energy and work are not the same thing. And you'll see this diagram again when we study gravitational potential energy. Very, very important. Okay? So again, energy and work both have units of joules, but these two are not the same thing. Okay. So in this little GIF, I have a little stick man who's pushing a crate, okay, starting at 0 meters with a constant applied force to the right. And obviously that crate speeds up, it accelerates to the right, okay? If I put some numbers in here, what we can do is we can actually talk about the work done, okay? So let's say that the total force is 20 newtons, and let's consider him moving it over a distance of 6 meters, okay? In this case, W equals Fs cosine theta, which is 20 times 6 times cosine of 0, which is, of course, 1, which is 120 newtons, okay? So it's that simple, really. It's pretty easy, okay? Really, all the IB kinds of questions that you'll get on work will be fairly straightforward, okay? Let's go back to the girl in the suitcase, and let's put some numbers to it. So she pulls on the suitcase with a 45 Newton force. The angle is 50 degrees, and she pulls it 75 meters through the airport. What's the work done? I got 2,170 newtons. So go ahead and make sure that you can do that problem correctly, okay? And a couple of demos I'll do in class for you. Okay. Couple of super important reminders. The term work was coined as weight lifted through a height, okay? And the joule is the SI unit for energy and work, but they are not the same thing, okay? Now, when you lift something, you're doing work against gravity. So if I lift my calculator from here to here, I'm applying a force upwards, and that force is countering the force of gravity pulling it down, okay? It turns out that if I move it from side to side, okay, I'm actually doing no work. I'm actually doing no work against the force of gravity because the force that I'm applying to lift it up is exactly perpendicular to its displacement, which is then horizontal. Okay, so this can be seen in the following example. This man holding a bag of groceries here, and he's walking with the bag of groceries to the right. It looks like that's his displacement vector right there. Turns out the man does no work on the bag of groceries because the force that he applies is to counter the force of gravity, or the weight, which is, of course, exactly perpendicular to the displacement vector. So there's no work done on the bag. Now, if you were to ask the guy, did you do work on the bag of groceries, he'd be like, yeah, because I'm really tired, I'm sweating, it's got, what did you buy? This is super heavy. But in fact, in a physics sense, he did not do that. Excuse me. So in picking up the bag from the floor to a height h, the man exerts a force equal to its weight. That's a simplifying assumption. When you're picking it up, you're actually accelerating it slightly upwards. So the force that you apply is greater than its weight, but a simplifying assumption that we always use is that the force with which you pull it up is equal to its weight whenever you're lifting something up. The total work done is the force times displacement, which is W times S, which is, of course, mgh in this case. Okay. Turns out this is exactly equal to the potential energy given to the bag. Gravitational potential energy. We'll talk more about that later. Okay? All right, to expand and reiterate, if you lift something straight up towards upwards a distance h, the work you do is mgh. Okay? All right? If you bring it back down to exactly where it started, it turns out you've done no work because your displacement is then 0. Okay? If something falls a distance h, the work done by gravity is also mgh, and it's actually negative mgh in this sense because it's opposed to the it's actually opposed to the work that you do on it. Okay. So here's the video, that funny video of the guy dropping, these guys that drop all this stuff off of buildings and take slow-mo videos of them smashing. This is a bottle of champagne. If we assume that the bottle of champagne is 2 kilograms and the height of the building is 35 meters, okay, the work done by the guy to carry the bottle to the top of the building from the parking lot is equal to positive 690 newtons. The work done by gravity to bring the bottle back down to the parking lot is negative 690 newtons. So again, there's your positive and negative, showing that those two, that in either case, work is done by a different entity. Okay. Now, if you've ever gone hiking, and you've gone out all day, you've climbed a mountain, you come back to your car, it turns out you've done no work at all, okay, because your displacement is 0. Now, you've done a lot of work if you've lifted your pack all the way to the summit of a mountain, but if you come all the way back to your car, you've done no work at all, which is counterintuitive because you feel really tired like you've done lots of work, okay? So, work is determined only by a vertical distance or the elevation of the hill and the weight of the pack. No work is done on the pack if the hiker ends up at the same elevation as where he started. Okay? All right. Here's an example about a water skier. Go ahead and try this one on your own. Okay, so the water skier is moving. The velocity is parallel to the boat, but there's a force on the tow rope that's actually at an angle of 37 degrees as shown. Okay, determine the work that it does in 12 seconds. Okay, so the first thing I want to do is I'm going to draw the tension vector and the displacement vector as shown. So the distance traveled in 12 seconds. That's pretty easy. Because I know velocity and time. I got a distance of 111.6 meters. So the work done is then quite simple. I got 12 kilojoules because work is Fs times cosine theta in this case. So the trick to this one is to find out, you're not given the displacement, but it's pretty easy to figure out. Okay? Just want to make a little note about time and work. Okay? If something does a certain amount of work in less time, then we say that that thing is more powerful, right? Turns out that power is, in fact, given by work divided by time. Okay, it's also given by energy divided by time, which we'll talk about that later, so you don't really need to worry about that right now. Okay, here's another example of a donkey pulling a pretty heavy crate. Go ahead and pause the video and try this one. Okay, so donkey does 800 joules of work. So now you're given the work and the distance and the mass of the crate. Determine the coefficient of kinetic friction between the crate and the ground. Okay, this is a little bit tricky, but if you see my reasoning, I think it will make sense. Remember that friction, kinetic friction is mu sub k times F sub A, which is mu sub k times mg. Okay, and I've drawn that vector right there for you. Okay, it's moving at a constant velocity, so the lengths of these two vectors are equivalent. Okay, W equals Fs, which in this case is mu sub k mg times s, and all you do is you solve for mu sub k, and I got 0.33. If the crate is pulled over a distance of 5 meters in 5 seconds, determine the power supplied by the donkey to pull the crate. Okay. Now, in this case, it's work per unit time, which is power. 800 divided by 5, it's 160 joules per second. Turns out that a joule per second is also equal to a watt, but again, you don't need to know that right now. We'll study that when we talk about power. Okay. Now, I'm going to talk about force displacement graphs. These are really important graphs because they allow us to figure out the work done in a situation when the force applied is not constant, such as in the case of springs being stretched. Okay, so a graph of force against displacement might look like this. Okay, so here I have F cosine theta on the y-axis and I have displacement on the x-axis. Don't be thrown off by the fact that cosine theta is part of the labeling for the y-axis. That just ensures that we're talking about the parallel components of F and S when we're graphing, which of course are the only two components that actually matter when you're talking about work. Okay, turns out that the area between the graph and the s-axis is the total work done. Of course it is, because the product of the y-axis term and the x-axis term, F times S, gives you work. Okay, and this area can be either positive or negative. Okay, now when the force applied is constant, such as it is from 10 meters to 20 meters, it's easy to find the work done. When it's not constant, it's harder, and you have to use an Fs graph to find W. So for example, in this case, the work done to move it from 0 to 10 meters, which of course is this triangle right here, okay, the area of that triangle, I got 50 joules. To move it from 10 to 20, which is the area of that big square, I got 100 joules, and of course from 0 to 20 would be just the sum of those two pieces, which is 150 joules. Okay? Okay. Try example 4 on your own. A little bit trickier. Okay, so this is a force displacement graph for two different bows, as in a bow and arrow. So if you look at the video of this guy pulling this bow, pulling the string back, okay, see he's applying a force on the arrow over a distance, right there, okay. Now, it takes different amounts of work to pull different bows back certain distances, right? Of course, because the bow, one bow, the wood could be different, the string could be stiffer, whatever, okay. So these are two different graphs for two different bows, bow 1 and bow 2, okay? Which bow requires more work to pull it back a distance of a half a meter? Well, sorry, this should be meters, not centimeters, okay? You can see that the area under bow 1 is greater than the area under bow 2, so therefore it's going to take more work to pull back bow 1. But you have to figure out in this problem the actual numbers because they ask you to estimate the additional work required for the bow compared to the other bow. So bow 1, I got 87.5 joules. That's simple. It's the area of that triangle. For bow 2, it's a little bit trickier. Okay, you have to do some estimation here. I estimated that there are about 29 squares underneath bow 2. So if that's the case, then the work done for bow 2 is about 58 joules. So of course, the work done for 2 is less than the work done for 1. If we estimate it at 58, and your answer will probably be slightly different, the additional work required is about 29.5 joules for bow 1. Okay, if you think back about springs and Hooke's law, that sort of stuff doesn't go away. In fact, we're going to study them even more when we talk about simple harmonic motion, okay? But I want you to recall specifically that F varies as S varies, okay? Remember there's the negative sign in there too, but we're not going to worry about the negative sign here. We're just going to say F equals Ks because we care about the magnitude of the work done, okay? So to find the work done in extending a spring from its unstretched position to a value x, what we would do is we would analyze the Fs graph, and it would be, of course, the area, this gray area as shown here, okay? Now, the height of the triangle would be kx, right? Because F is kx. Okay, there we go right there. The base is x. So the area would be 1/2 kx squared of a triangle, okay? Because that's 1/2 of F times x, okay? The work to extend a spring from position x1 to x2, as shown here, is 1/2 k times x2 squared minus x1 squared, obviously. So it's the big area, big triangle area minus the little triangle area, okay? And I just want to point out something in your data booklet that you need to be aware of from this point onward, and it is that they're saying that potential energy stored in the spring, okay, is equal to 1/2 k delta x squared. And I want you to notice the similarity between this equation and this equation. They're not quite the same, but they're quite similar if you think about it, okay? This is not delta x squared if you work it out mathematically. Anyway, you just need to be aware of that, and we'll use this equation later on, okay? Okay, so one more example of a mass on a spring. This is experimental data from the lab that we did with the spring extension and the weight or the force applied. And I want you to figure out the amount of work required to stretch this spring shown from 5 to 15 and 15 to 25, okay? Go ahead and do that. Okay, you might notice that I've drawn some shaded areas here. The red shaded area corresponds to the answer for part A, and the green shaded area corresponds to the answer for part B. A curious thing that you're probably wondering is why doesn't the shaded area go all the way down to the x-axis? And the reason is because we need to consider only the area, the shaded area down to a horizontal line that goes through the y-intercept. And I'll explain that a little more in class to you guys. Okay? Anyway, so the red area, okay? Oh, first of all, note that the gradient is the spring constant, which is 25.8 newtons per meter, which is right here. Okay, all values in this case are approximate because this is experimental data, okay? So here's the area, by my reckoning, of the pink area here. I got 0.185 joules, okay? If you use the equation that I introduced in the previous slide, you get 0.161 joules, okay? That's a little bit different, and that's okay because remember this is experimental data and this is actually a best fit line, okay? All right. From 15 to 25, that's the green area, I got 0.510 joules. And again, using this equation I introduced in the previous slide, I got 0.516 joules. They're in pretty darn close, good agreement there, okay? But just remember, all values are approximate because we're using experimental data.